When Guglielmo Marconi transmitted the first radio signal in 1895, he tied the future of wireless communication to a narrow slice of the electromagnetic spectrum. For decades, that spectrum comfortably supported our hardware, but the rollout of cellular networks and mobile computing rapidly saturated those available radio frequencies. Today, billions of active devices crowd the 2.4, 5, and 6 gigahertz bands, resulting in severe signal interference. Furthermore, strict international licensing and physical wave properties impose a hard limit on data capacity. While modern standards attempt to push higher speeds through these bands, doing so requires increasingly complex hardware to manage noise. To scale wireless infrastructure reliably and efficiently, we have to look toward a higher, uncongested portion of the spectrum. This chart shows the electromagnetic spectrum. By moving past microwaves and infrared, we arrive at the visible light spectrum, a massive, uncongested block of bandwidth spanning from roughly 430 to 770 terahertz. This is the operating domain of Light Fidelity, or Li-Fi. Instead of antennas, this system converts standard LED illumination infrastructure into wireless data links. By rapidly modulating the electrical current supplied to a light-emitting diode, we can fluctuate its light intensity at extreme frequencies. These pulses happen so quickly that they remain entirely imperceptible to the human eye, which registers only a steady glow. Operating in this unregulated spectrum allows Li-Fi to bypass radio bandwidth limits, yielding theoretical data rates of up to 10 gigabits per second. But realizing that potential requires engineering an entirely new physical layer architecture. The most basic geometry of a Li-Fi link requires two physical components: an overhead transmitter generating the signal, and a grounded receiver capturing it. The transmitter relies exclusively on LEDs, rather than incandescent or fluorescent bulbs. LEDs convert electrical energy into optical energy with high efficiency, and critically, they can be modulated at the megahertz and gigahertz frequencies required to encode digital data. As modulated light strikes the semiconductor material inside a pin photodiode, it generates an electron-hole pair, converting photons into a measurable electrical current. In weak signal environments, avalanche photodiodes replace them. The initial photon impact triggers avalanche multiplication, applying gain to amplify the output. But while the LED and photodiode successfully establish a raw physical bridge, simply detecting the presence or absence of photons cannot encode the complex data density required for a modern network. This timeline visualizes the most basic method of optical data encoding, on-off keying, or OOK. When the light intensity is high, the receiver registers a binary 1. When it drops, it registers a 0. OOK is highly inefficient, leaving vast amounts of optical bandwidth unused. To improve efficiency, engineers employ pulse position modulation. Instead of reading amplitude, data is encoded based on the exact time slot a single pulse arrives. This time domain modulation conserves energy, since the LED remains off for longer durations, but it introduces a severe engineering challenge. The transmitter and receiver must maintain rigorous, microsecond timing synchronization to prevent total data loss. Even with perfect synchronization, all time domain modulation techniques eventually hit a hard throughput ceiling, well below the gigabit threshold. If manipulating a single stream of light over time tops out in the megabits, what signal processing architecture is required to extract 10 billion bits per second from a single source? The solution is orthogonal frequency division multiplexing, or OFDM. The bandwidth is divided into narrow orthogonal subcarrier waves, parallelizing transmission so multiple data streams flow simultaneously. But when subcarriers align, they create jagged amplitude spikes, causing a high peak-to-average power ratio. OFDM successfully breaks the gigabit barrier by maximizing the visible spectrum, but processing those complex high-power waveforms offloads a massive computational burden directly onto the receiver's hardware. Achieving 10 gigabits per second requires ideal laboratory conditions. In the real world, Li-Fi is strictly a line-of-sight technology, leaving it uniquely vulnerable to everyday environmental physics. The receiver must isolate the LED beam from ambient sunlight and fluorescent light. If this noise saturates the photodiode, the signal-to-noise ratio drops, masking the data. Also, as light reflects off walls and desks, secondary signal versions arrive delayed, causing destructive multipath interference. Left unmanaged, ambient noise and multipath fading cause the bit error rate to spike. To salvage the data stream, Li-Fi systems mandate the use of forward error correction, injecting mathematical redundancy into the signal so the receiver can rebuild corrupted packets on the fly. Ultimately, Li-Fi's extreme speeds are fragile. Because the physical environment strictly dictates the capacity of the octal channel, advanced error correction and signal filtering are non-negotiable requirements for a stable link. By placing the radio frequency architecture next to the visible light architecture, we can isolate their distinct utilities. Because Wi-Fi operates in a narrow, congested RF band, it routinely battles interference that degrades speed. By utilizing the massive, uncongested terahertz spectrum, Li-Fi delivers dedicated data streams with latencies dropping to 1 millisecond. But the defining difference is propagation physics. Wi-Fi penetrates physical structures. Li-Fi stops entirely at the walls, confined perfectly to the space it illuminates. While wall penetration gives Wi-Fi its convenient range, it also creates an attack surface. RF signals can be intercepted from outside, leaving networks vulnerable to eavesdropping and man-in-the-middle attacks. By contrast, Li-Fi enforces strict physical layer security. Because the signal cannot escape the room, intercepting the data stream requires an attacker to physically stand inside the cone of light. This reveals the true utility of the technology. Li-Fi is not built to replace ubiquitous Wi-Fi. It is a specialized architectural layer designed specifically for environments where radio spectrum is exhausted or where physical data security is paramount. This strict containment makes Li-Fi ideal for critical deployment zones. It provides interference-free networking in hospitals packed with sensitive medical equipment, secures communications in military installations, and supports dense device arrays in smart factories. By leveraging the LEDs we already use to light our rooms, engineers have successfully converted basic illumination infrastructure into a complex gigabit-scale data network. The radio frequency spectrum carried us from Marconi's telegraph to the modern internet, but as those frequencies reach their absolute physical limits, we have to look higher up the spectrum to scale global communication. Moving data through the physical layer of visible light allows us to break through the congestion. It is the necessary next step to ensure our wireless infrastructure can support the data demands of the coming decades.